All right, welcome back. We're working on example 4 from 1 day 14, section 3.4. And this is from Math 360. And the problem said some biology students were checking the eye color for a large number of fruit flies. The individual fly, for each individual fly, let's suppose the probability of white eyes is 1/4 and the probability of red eyes is 3/4. And that each of these observations are independent Bernoulli trials. The probability that, uh, or what is the probability that at least 4 flies have to be checked in order for a white eye color to be observed? Okay. So the probability that at least 4 need to be checked would be the probability that x is greater than or equal to 4, since x is the observation of the white eye color. Which is, of course, strictly greater than the probability that x is strictly greater than 3. And so the probability of x being greater than 3 is going to equal the probability of q to the third, which is the probability of not. And so you're going to get that it's 3 out of 4 cubed, which is 27 over 64. Therefore, the probability that at most 4 flies have been checked for eye color to observe a white fly is given by P of x less than or equal to 4. So again, this is the probability that at most 4 flies have been checked for eye color to observe a white eye fly. P is less than or equal to 1 minus q to the 4th, which is equal to 1 minus 3 over 4 to the 4th. Which is, put this into calculating 256, 175 over 256. Okay. All right, so we have the probability here that at least 4 flies are checked to observe the white eye color is the probability of x greater than or equal to 4, which is equal to the probability of x being greater than 3, which is equal to not seeing white eyes for the first 3 trials, and the probability that that at least 4 or no more than 4 flies have been checked for white eye color is the complement of that. So the probability that the first fly with white eyes is the 4th fly considered is P of x equals 4, which is q to the 4 minus 1 times p, which is 3/4 to the 4th, and 1/4, which is 27 over 256. That's exactly on the 4th trial. Okay. What else can we do with this? So we could say that P of x equals 4 is equal to the probability that it's less than or equal to 4 minus the probability that of x being less than or equal to 3. So everything before 4 and then everything before 3. This is easy to think about. It is all probabilities before 3 and all probabilities before 4. So if you subtract off this length from this length, the result you get over is just the probability of 4, even though thinking about it in terms of lengths. I hope that makes sense. So we've answered probability of at least 4, probability of at least 4. We've looked at probability of at most 4, and the probability of x equaling exactly 4, and another way of seeing the probability of x equaling exactly 4. So I hope that helps establish then some connections or some ideas. And so this is really nice, simple example to kind of introduce then the following concept, which I wanted to illuminate a little bit more without having to write all the notes for it. So this is the end of that example, but let's look at the reason for like why do they call this a the negative binomial. remember in the notes I said when r is equal to 1, it's called the geometric because you get a geometric series as a result of that. So that's cool to keep in mind. But let's see, what should we call it? Got G already used. If we try H of W, that seems reasonable. So what if we consider 1 minus W to the negative R? Uh, then the binomial here of 1 minus W with the negative exponent of R with negative exponent of R. That's just restating this. Uh, we can expand this. This is a series when we have the right values of W. In other words, when W is between. Um, let's see. I'm going to say we can expand H of W if the absolute value of W is less than not less than R, less than 1. In other words, as long as we're not dividing by 0, the radius of convergence for this series is going to be the absolute value of that from -1 to 1. So as long as W is within that range, then the series converges, and we can write it as 1 minus W to the negative R is equal to the sum of k equals 0 to infinity of h to the k at 0 over k factorial W to the k. And we can make the connection that if we let x, let's see, well, before we do that, let's do something with this. So the coefficients here can be written using the binomial expansion. You can say that k equals 0 to infinity of what r plus k minus 1 to r minus 1 to the r minus 1 W to the k. And again, W is still bounded between 1 and -1 here. Okay. And now this looks like it's in a form that we can better serve. So let's let x equal k plus r here. K plus r, we're gonna let x equal that value. And then that means that k is equal to x minus r. Okay, so that implies that x is equal to, or k is equal to x minus r. And so we can rewrite this expression up here as 1 minus w, the negative r, is equal to the sum of x equal to r to infinity of r plus x minus r minus 1, r minus 1. Okay. And then let's see. That allows us then to do this nifty little comparison that x is equal to r to infinity of x minus 1 over r minus 1, let's see, w to the x minus r. All right. The sum end of which, with the exception of the factor of p to the r, is a negative binomial when w is equal to q. So if this is equal to q, then it's really close to a negative binomial. In particular, notice that the sum of the probabilities for the negative binomial is 1. Okay, so the sum of the negative, and why is that, you might ask? Well, we're running out of space here, so let me throw off another sheet here and finish this off. So if we let going back to our function g of x, so the sum of x equal to r to infinity of g of x is equal to the sum of x equals r to infinity of x minus 1, choose r minus 1, p to the r, q to the x minus r, which is equal to p to the r times 1 minus q, the negative r, which is equal to 1. Okay. Nothing to say about that. Let's see. From this, we can show that the mean of this negative binomial is equal to r over p with our definitions here of r and p. And the variance is going to equal r q over p squared. Notice if r is equal to 1, this becomes 1 over p, and this becomes 1 minus p over p squared. For the geometric sequence, which is what we would expect from our intuition. It illustrates that the probability is 1/6 when we expect the average to be, at a fixed tile, the first success would occur. We can find the moment generating function for the negative binomial. Let's see, I guess that would be important to maybe talk about too. So the moment generating function for the negative binomial is the sum from x equals r to infinity of e to the tx times f of x, which we just saw, which is like minus, well, I guess we call it g of x, but you get the idea. R minus 1, p to the r. I'll write 1 minus p to kind of keep it in the same flavor. X minus r. Okay, so you can factor out a factor of, looks like, we'll have these to an r. Yeah, so that's the moment generating function. So you can calculate the derivative of this and the second derivative and use those to arrive then at these results here. So I think that's going to be a fun little exercise to explore. It may be helpful to worry about how do you move that out of the series form. In other words, is there a way to write that in a perhaps a closed form notation? And let's say there's a nice little trick to doing that. So I'll leave that open for you to explore if you'd like. But I hope this was helpful, and I'll definitely see you in the next video.